Hello everyone, in this video we are gonna solve a problem that involves finding the frequency response of the mass damper system. So here we have this system. Our first task is to find the transfer function, and transfer function here is defined as omega s over ts. T is the input torque and omega is the rotational speed that this cylinder would get after the application of the torque. Our first task is to draw a free body diagram for this system. So the free body diagram of this system would be simple because we only have one load being applied here. We have T, and the only thing that is resisting this torque will be this damper. This is a rotational damper. So it's gonna have a torque opposite the direction of our input torque, and the value would be c theta dot. If you remember, linear dampers, they would create a force for us cx dot, the displacement rate. Here is the rotation rate or rotational speed. So now we need to write our differential equation. So for rotational component, the summation of moment is I theta double dot. Here the moments that we have is T minus C theta dot would be I theta double dot. If I rearrange this, I would get I theta double dot plus C theta dot equals T, and instead of theta dot, I know that would be omega, and theta double dot would be omega dot. So I can write I omega dot plus C omega equals T. And if I take a Laplace of this to find a transfer function, that was one of the definition of transfer function, that it should be in Laplace domain, would be IS plus C omega s would be equal TS. Therefore, the transfer function would be the output over input, and the output for us is omega s over TS. Therefore, I have 1 IS plus C. That would be the transfer function. Also, I have the value for I and C, so I can plug it in. So if I show transfer function by T, it will be 1, 2s plus 4. So this part is not new. We knew how to find transfer function. But the interesting part is that to find the steady state response, if we have this input. Let's say this input is being applied to our system, and then this input has multiple components. It has a fixed value, a constant value, and then we have two functions of time, sine and cosine here. We can use the frequency response definition that only the magnitude and the phase would change during the frequency input. So if we want to find the steady state, I have 30. The only thing that would change would be the magnitude. And the frequency here is 0, is a constant value. So M0 plus 5. I have to multiply by the magnitude. The frequency here would be 3. So remember, the function frequency is here. That's the frequency for us. That's the frequency for us. And this one didn't have any frequency. That's why the frequency for this case was 0. And then I have sine 3t, and then plus the phase change, and then 2m5 cosine 5t plus the phase change. So my job is to find m0, m3, and m5 in addition to phase changes. So I have to find 5 unknowns so I can find a steady state response of the system. So we have the transfer function. We can find this change in amplitude. Or simply you need to replace our transfer function with the s in transfer function with j omega. Here we have 3 different j omega, so we're going to replace it with 3 different values. You need to pay attention to that. So I can start with m0. I just need to plug in 0 for s. If you plug in 0 here, 2s plus 4, that would be 1 over 4 or 0.25. That's the first unknown. The second would be m3. And then I have to put the 3j. So I replace all s with 3j. If you look at the transfer function, would be s would be 3j plus 4. And then we're talking about the magnitude. So here I have 4 plus 6j, so 4 squared plus 6 squared, I would get 0.1387. And then I have to find, that's the other one that I found, I need to find the phase change for this case, which should be 0 because the numerator is 1. The denominator, I go negative, tangent inverse of the imaginary part over the real part, 6 over 4. I get the negative 0.982. 0.982. So I found this value as well. So far this is resolved, this is resolved, and then phi3 is resolved. I need to find m5 and phi5. Let's go and do that. So we just need to replace s with j omega. Here omega is 5, so t5j. The process might be a little bit tedious, but you would immediately see that it's pretty straightforward. Square root of 4 plus 10, 0.0928. And now I need to find, I found this guy, I need to find the phase change would be 0 minus tangent inverse of the imaginary over the real. So 10 over 4 this time. And the value that I get, let me move up more space here, negative 1.19. And that's in radian. So now I can replace everything. Now I have all the value. I would say the steady state is 30. M0, I found it to be 0.25 plus 5. M3 was 0.1387. Sine of 3t minus 0.982 plus 2, and M5 was 0.0928 cosine 5t minus 1.19. So you can see the smaller value have more significant effect for us. So when you get a magnitude change of a small value, don't think that's negligible. That actually makes the largest difference because we are multiplying the magnitude by that fraction. I can also simplify it. It would be 7.5 plus 0.693 sine 0.982 plus 0.1856 cosine 5t minus 1.19. So this is the response of the system. It's the same format as the input, just the amplitudes have changed, these values have changed, as well as we have introduced some phase change here, as you can see. The third part of the problem is interesting. Here, the plot or the Bode plot is given to us, and we want to do the same thing. We want to find a steady state. but this time using the Bode plot. So what is the Bode plot? It tells us the change in magnitude for any given frequency. So here is almost 0. So that's the change in magnitude that we have. So basically that is M0 for us. Here we have the change in magnitude for the frequency of 3. So basically this is M3. I mean, maybe we shouldn't call them M3 because they're in decibel. So we have to change that. And then this is M5 for us. And same thing here. We have the phase change. So we have 0. That's approximately 0. That's the reason that it's 0.1 is that you can't really click it. It's a logarithmic scale. It starts in 0.1. And here, that's the value for 3. And that's the value for 5. That's 4.99. So here I have the, let me do it again here so you can see it better. So we're gonna do the same thing but using the Bode plot. So Bode plot is gonna give us the change in magnitude and phase. So if we don't have access to the transfer function, we can use Bode plot to find the change in magnitude and phase. So you can think of Bode plot as replacement for the transfer function because it tells us the response of the system for a range of frequencies. So the steady state response, we knew that it's just a function of the input. That's what we knew. We have 2 M5 cosine 5t plus phi5. So we found the value of M0, M3, M5, phi3, phi5 by putting j omega, or depending on the omega, 3 omega, 5 omega, 5j, 3j into our transfer function. But we do not need to have access to the transfer function, even if we don't have the transfer function, but we have the Bode plot that tells us how the system responds. The Bode plot is telling us the magnitude at different frequency, the magnitude difference at frequency of 0, at a frequency of 3, and a frequency of 5. The only thing that we need to pay attention is that the magnitudes are given in decibels, so we need to make the changes. So for the first one, we have the decibel value of it. So for M0 is negative 12.1. So if we really want to find M0, if I divide both sides here by negative 20, by 20, and then here 10 should be raised to the power of negative 12.1 over 20 to get the M0. So M0 would be 10 to the power of negative 12.1 over 20. And that value would be 0.25. For the phase, the Bode plot directly tells us the phase. We don't need to make any changes to that. And we can do the same thing for other values. 20 log 10 of M3 would give us the decibel value that the plot is providing. I'm just changing decibel to the magnitude. MATLAB does that for you as well. So you can use the Bode plot and then do decibel to magnitude function. That would be 10 negative 17.2 divided by 20. So 10 to the power of negative 17.2 by 20 would give me 0.138. So if you pay attention, these are the exact values that we got using the transfer function. Here I have the phase. I have to make a change to radians because the rest of the function is radians. So I have to multiply it by pi over 180, which I get. Let me write it here. Let me see if I have a space here. Negative 0.98. So there is a change to do for phase as well, changing it from degree, this is a degree, to radian. There is a way to plot Bode in radian as well, but degrees is more common, and the default of MATLAB is in degrees. Do the same thing for M5. That's negative 20.7. So M5 means the magnitude at the frequency of 5 radian per second would be 10 to the power of 20.7 divided by 20. The value 0.092. The phase change, I have the value negative 68.1 degree multiplied by pi radian over 180 degrees. So that changes from degree to radian. That would give me the value of negative 1.19. So these values that I found are identical by using the transfer function. So Bode plot was a replacement for transfer function because it tells me the change in magnitude and phase for a range of frequencies. So for any input that you give me, if I have the Bode plot, I can tell you the output. So Bode plot is full of information for me that is going to be very helpful for finding the frequency response. And MATLAB has a built-in function for that, is Bode. Numerator, denominator will give you this plot.